thanks for coming back. Okie doke, jumping straight in. Let's imagine that we have access to the world's largest and smoothest ice rink. The ice is perfectly flat, flawlessly finished. And so I'm gonna make an executive decision as the leader of this thought experiment to say that because this ice is so perfectly smooth, we can ignore friction, or assume that any object that slides on the ice won't experience any resistance due to friction between its own surface and the ice. Why? Would this ever happen in real life? Nope. There are some super advanced technical materials that come close to this, but not actually to the point where there is zero friction. Later, we'll talk about just what friction is and how we analyze it. But for now, let's stay in this little scenario. And if you're thinking like, Bailey, why are we dwelling on some theoretical situation that we'll never encounter in our actual lives? This seems irrelevant. Well, you're right that we're not specifically modeling some everyday situation. But similar to our discussion on imagining interactions in deep space where we don't have to think about gravity, there are instructional benefits to thinking about this. In physics, we discuss these theoretical situations just so that we can isolate certain ideas and see how they work without the influence of other outside factors. It's like an unadulterated view of a specific concept. And then we can take what we learn from there and have that underlying knowledge in a real-world situation. And then we can compare how they're similar and different and draw conclusions about those other things that do take effect in real life. This is pretty common in physics. And so while learning and practicing, you might find yourself reading things like, assume the surface is frictionless, or ignore air resistance. Those kinds of phrases are a little weird, I admit. I've been in physics for a while, and by this point, I don't think much about them. But to people who are engaging in physics more casually, they might get a little thrown, and that's totally normal. Actually, research has shown that weird subtleties like these, along with the kind of stilted language that's often used in physics, and has been coined physics text, can be a real barrier to understanding for physics students. That's why I'm taking the time to talk specifically about this. Physics educators like me do think it's a good idea to engage with these theoretical no friction, no gravity, or no air resistance situations. But it's also good for you, the student, to know why we do this. It's not meant to throw you off or see if you're on your toes or whatever. And as a physics instructor, when I say something like ignore friction, I don't mean that friction isn't real. In fact, in a way, I'm acknowledging that it would, in real life, have an effect on what we're studying. What it means is, just for the reasons that I just mentioned, that I want you to isolate any potential effects of friction and put them to the side for the moment. And you know what? While we're at it, I'm going to cancel air resistance for this ice rink too. No resistive forces. All right, so we've got this flat, frictionless, icy surface. Does anybody remember the Magic School Bus episode where they tried playing baseball without friction?
Seatbelts, everyone!
In the episode, they realize that they can't walk or run without friction. They can only push off of other things, and everybody's slamming into each other.
Hi!
Seatbelts, everyone! Anyways, say there's a hockey puck gliding on the ice. So long as nothing gets in its way, is the puck's motion going to change? Do you think it's going to slow down? Now, normally in actual everyday life, when we see an object sliding across a surface, we expect to see it slow down at some rate, depending on what the object and what the surface is, and eventually stop. Because friction is real. Friction is a thing all around us. Things slowing down to a stop is the pattern we observe basically 100% of the time here in our daily interactions with the things around us. And it might seem like, well, I don't really stop to think about friction like you, weirdo. It's just kind of something that happens and I don't pay it any mind. I don't sit there thinking about whether or not an object is going to stop moving. But the thing is, whether we're conscious of it or not, we start building an intuitive sense for the way things around us move and interact from the time we start observing things at all. From birth, our brains are working to detect patterns and form some understanding of how to get things to do what we want them to do. And these patterns of thinking are very deep-seated. We interact with objects every day, pretty much all day, and all that time our brain is storing information about how these interactions go. So, When we live our entire lives observing things moving on surfaces with friction present, we start to think that it's just the natural order of things that are moving to stop moving. We think that an object moving on a surface wants to stop, because in order to keep that object in motion, say moving at a constant speed, we have to keep pushing it along. Because of this, it's very common for people learning physics to think that a constant force is needed to keep an object in motion, moving at a constant speed. Now, let's return to our example of the hockey puck sliding on the frictionless ice, and say that the hockey puck is moving along to the right at a steady speed. Nobody's touching it, there's no air affecting it, there's nothing in its way. If it is the case that constant force is needed for constant motion, what is the net force acting on the puck? We can try to think about all the possible forces acting on the puck. We know that it's sliding along on ice. Now, we said no friction, but besides that, we know that the puck is still touching the surface of the ice, right? So there's an interaction between the puck and the surface. The surface exerts an upward force on the puck. So is this an unbalanced force acting on the puck? If it were, wouldn't we expect to see the puck start accelerating in that direction? The puck doesn't just start lifting off the ice. So can you think of any other interactions that would act to balance out that upward force? Well, we're talking about a hockey puck on an ice rink. We can assume we're on Earth, so there's an interaction between the puck and the Earth. We know that there's the downward gravitational force of the Earth acting on the puck. This downward force balances the upward force, and so there's no net force in the up or down direction. And that makes sense. As I pointed out, the puck isn't accelerating in the up or down direction. Is the puck accelerating at all? Its speed isn't changing, and its direction isn't changing. If it's not accelerating, then there must not be a net force acting on it. Remember Newton's second law. When a net force, a total unbalanced force, acts on an object, the object accelerates in the direction of that net force. If there is no net force, there is no acceleration, no change in motion. But this doesn't mean that there's no motion at all. You remember the term, an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an unbalanced force? That is Newton's first law of motion, which is also called the law of inertia. Inertia is just the tendency of an object to resist change to its motion, or basically to not accelerate on its own. In order for an object to accelerate, be it slow down, speed up, or move in a curved path, there absolutely must be an unbalanced force acting on it. If the net force on a stationary object is 0, that object is just going to sit there. If the net force on a moving object is 0, then that object is just going to keep moving at the same velocity, the same speed, same direction. So, hear this. Motion does not imply force. Just because an object is moving doesn't mean there's a net force acting on it. There may not even be any force acting on it, like for the case of something out in deep space, which really does happen. There are actual objects out there traversing interstellar space. Again, we have to remember that the laws of physics are universal, and we humans who experience our lives in the specific environment of Earth and everyday objects and things like gravity, friction, and air resistance, we're used to seeing certain patterns. So much so that we think to explain those patterns as just the natural tendencies of objects. So, we should recognize these patterns, understand why we see them so often, and then break them down into separate influences so that we can get down to the true nature of physics. Let's talk about resistive forces. Let's get into it. First, friction. How would you define friction? Friction conjures up images of sliding. Friction acts to make slidey stuff slide less, no? Friction is what we call a resistive force, where resistive just means that it acts in the direction opposite to the intended motion of an object. Say you try to push a box across the floor. What does friction do in this situation? It feels like it's almost pushing back, right? Making your job harder. But friction isn't always working to make your life harder. We actually need friction to do everyday stuff, like walk, or grab things, or get around by bike or by car. Remember the magic school bus debacle?
Not a good idea!
Friction works for us in many ways, by literally allowing us to get a grip. Friction is a force that opposes the motion between two surfaces. I say two surfaces. We always got to remember that any force ever is caused by an interaction between two objects. So with friction, the amount of force, the amount of friction that occurs depends on some properties of the two surfaces. It's not just about one single surface. Check out our chair here. When we first got it in our apartment, it would slide around on our wood floor anytime someone sat down in it. So we put little rubber sticky things on the bottoms of the legs, which works great. The slidey thing wasn't just a problem with the wood floor, and it wasn't just a problem with the wooden legs of the chair. If the wooden legs were on carpet, the chair probably wouldn't move around, and we wouldn't have needed the rubber pads. It was a problem with the wood floor and the wooden legs of the chair. Those surfaces don't have much friction between them, but the wood floor and rubber do have a lot of friction between them, so any motion between those two surfaces is met with a lot of resistance. Think about running on a wood floor. You might be fine to run across that wood floor barefoot, but put on some fuzzy socks and try again, it's a different story. One incredible piece of wisdom that Quinn has imparted to me, bless his engineer soul, is a life hack for opening jars. If you're struggling to get the lid off a jar, and God knows it's me every time, Quinn says to put a rubber band around the lid. This works because the amount of friction between your skin and rubber is much greater than the amount of friction between your skin and smooth metal. And you need that friction to resist the motion of your hand. It's not helpful if your hand is just sliding around on the lid. You need enough friction to actually grab and turn it. All right, let's look at a couple force diagrams to help us think about how friction acts on a given object. We'll start for the case of me pushing on a box. I am pushing it, so why isn't it moving? Friction, baby! Okay, so here's the box. I'm pushing on it to the left. Is this an unbalanced force? Well, if it were, then the box should be accelerating to the left, and we can see that's not the case. So the leftward force of my push on the box must be balanced by the rightward force of friction. Adding the force of friction to the force diagram, how does its strength compare to the force of my push? Remember, the box isn't accelerating, so the net force on the box must be 0. So any force to the left must be met by an equal strength force to the right. These forces are the same size. And get this, if I push more gently on the box now, so that the leftward force from my hand is smaller, the rightward force of friction actually gets smaller too. This might sound crazy, but what's the alternative? Say I push more gently to the left, but the force of friction to the right stays at that greater strength. We would have an unbalanced force to the right, and it would be pretty shocking if the box started moving to the right. I get that it might seem strange that this force of friction adjusts to the force it's opposing, but this is pretty similar to how the upward force supplied by a table adjusts depending on the downward force acting on the table. Newton's first law really guides us here. If the motion of an object isn't changing, we know that there's no net force acting on that object. But that doesn't mean there are no forces acting on the object. It just means that forces acting on it in any direction must be balanced. So now we can see why the box isn't budging. The force from my hand is balanced by the frictional force from the surface. Oh, pop quiz. Are there any other forces acting on the box right now? Well, the box is here on Earth, no? So we have a downward force of gravity acting on the box. But now our diagram shows an unbalanced force in the downward direction. This can't be right since the box isn't accelerating downward through the table. So that force must be balanced by an upward force of the same strength. That's the upward force exerted by the surface. Sweet. Next, let's think about an object that is in motion. We'll say this notebook on the floor. I give it a good push to set it into motion, and it slows down to a stop. While the notebook is slowing down, what is the direction of net force acting on it? Well, we can break out that truism from before. If an object is slowing down in a straight line, there must be a net force in the direction opposite to its motion. This makes sense with what we just learned. The notebook is moving to the right, and friction is acting on the notebook to the left. the notebook slows down because there's a net force acting on it in the opposite direction. What would I have to do to keep the notebook moving at a constant speed? I would have to push it, right? Say I'm pushing the notebook so that its speed is constant. How does the force from my hand compare to the force of friction from the floor? Would you say that the force from my hand is greater since the notebook is moving in that direction? Well, let me ask you this. Is the notebook accelerating? Well, its speed and direction are constant. It's not accelerating, so there must be zero net force acting on it. These left and right forces are balanced, and so the motion of the notebook doesn't change. Remember, if there's a net force, there must be acceleration. No acceleration implies no net force. And no net force doesn't mean no forces at all. It just means that any forces acting on the object are balanced. One more example before we move on from friction. Let's think about walking. When I walk, there's friction between my feet and the floor. I don't want my feet to just be sliding around on the floor without a grip. If I'm walking, moving forward, in which direction do you think friction acts on my feet? Well, remembering that friction acts to oppose relative motion between surfaces, we can think about what this relative motion would look like. When I want to walk or run or jump forward, I use my feet to push backward. Look what happens when I try to run on a slippery rug. My feet push it backwards, and that is essentially what friction is working against. Walking on the wood floor now, the force of friction acts on my feet to resist the backwards motion, which helps to propel me forwards. Cool, that's friction. Next, let's talk about air resistance. That's a buzzword for sure. In your head, how would you define air resistance? Well, we know that the term resistance in physics pretty much just means a force that's acting in the direction opposite of the intended motion of something. Like when you walk around in water, and it's really hard to get to where you want to go because there's a bunch of water you have to push through. Air resistance actually works a lot like this kind of water resistance. Air and water are both fluids. They both flow. They're made up of huge collections of particles that move pretty freely relative to each other. Of course, we can't see air particles, but we can swing our hands and feel the whoosh of air that our hand pushes out of the way. We can notice the same thing when we put our hands in water and whoosh them around there. A lot of particles get pushed out of the way, but they have all sorts of swirly, twirly tendencies, and the space behind our hand gets filled in with other moving particles. Now, obviously there are some huge differences between air and water. For one, water is much more dense. There's a lot more matter in a given space, and it resists our motion much more than air. Compare the experience of running in a swimming pool to running through air on just dry land. But thinking about the similarities between air and water will really help us here, since the denseness of water helps make the resistance it causes to an observer a little bit more obvious. So, open air, like water, is full of billions of particles, and for a moving object, moving these particles out of the way takes some work. So, anytime an object moves through air, it experiences air resistance because of an interaction between that object and the air. We can identify the Newton's third law force pair here. The object exerts a force on air since it's pushing air as it moves, and the air exerts a force on the object, a resistance. So, if an object is surrounded by air, is moving to the right, air resistance acts on the object to the left. If the object is moving up, air resistance acts down. Air resistance on an object just points in the opposite direction to its motion. Now, there are a few factors that determine the strength of the air resistance that acts on an object. And the nitty-gritty physics behind air resistance is a bit crazy. It's fluid dynamics. It's really chaotic. So we don't need to go there. Basically, all we need to know is that the strength of the air resistance depends on the speed of the moving object and the front-facing area of the object. So, the faster an object is moving, the greater the air resistance. Why? What is it about the speed of the object? Well, the faster an object is moving, the faster it needs to move air particles out of its way. And it's harder to do that quickly than it is to do slowly. We can use what we know about water resistance to illustrate this by thinking about entering a swimming pool. Imagine slowly lowering yourself down into the water, and compare that to jumping into the water from a diving board or a platform. When you jump from high up like that, you're going to enter the water with a lot of speed. This means that the water isn't going to have much time to get out of your way. This is why hitting the surface of water can be really damaging from great heights, like jumping from a bridge. When you're moving that fast, those water particles aren't going to move out of your way as quickly as you'd like them to. The water provides a lot of resistance to your body. A similar thing goes for air resistance. The air resists the motion of faster moving objects more than it resists the motion of slower objects. Next, the thing about area. I said front-facing area. In physics, we'd call this cross-sectional area, meaning, in this case, the area of the object that faces forward just in the direction of motion. It's why we make airplanes and vehicles with small, pointed, and curved shapes on the front, rather than a big flat surface like a sail that catches a bunch of air. Next time you're in a car going at a good speed, stick your hand out the window and compare the amount of air resistance you feel when your hand is straight up and down versus when it's horizontal. Nothing fundamentally changes about your hand. It's just that the way it's turned, it can either act like a sail, catching all that air with the front-facing area of your palm, or it can slice through the air with that much smaller front-facing area of just the side of your hand. And when you think about air resistance, you might think about the term terminal velocity, or the thing where an object falls with a sort of speed limit set by the upward force of air resistance. We won't really concern ourselves with terminal velocity in this course, but it's good to note that most everyday objects won't hit terminal velocity until they've fallen from a really significant height. A human, for example, needs to fall about 1,500 feet to reach terminal velocity, which takes about 12 seconds. So for the context of this course, we won't get into terminal velocity. But there is a lot to be learned about the rate at which objects fall. You might have heard the idea before that without the effects of air resistance, all objects fall at the same rate. How could this be? This goes against so much of what we know and expect about the way things fall in real life here on Earth. We'll throw it back to the days of Galileo and think about a feather and a hammer or gavel or whatever, and imagine we're dropping them in a vacuum, just meaning that there's no air in the space around them. We're dropping both objects, so they're starting from rest with 0 speed initially. When we drop these bad boys, they'll both fall side by side at the same rate and hit the ground at the same time. But how is this possible? They definitely have different masses. So doesn't Earth's gravity exert different amounts of force on them? Yes. The hammer has much more mass. It's much heavier, meaning there's a greater gravitational force acting on it. So why doesn't this greater force mean that it falls faster? It's because of its greater mass. Remember inertia. The more mass an object has, the more that object resists changes to its motion. It's harder to move a heavier object. It's harder to get a heavier object to accelerate in any direction, including down. So, because the hammer is more massive, because it's heavier, it takes more force to get it to accelerate, to fall at a certain rate. The feather has much less mass. It's much lighter, so not nearly as much force is needed to get it to accelerate. You know that if you had a hammer and feather both sitting on a table in front of you, and you pushed them both with equal force, the feather would respond much more readily to that force. In the case of falling objects, the applied force on the object is the force of gravity due to Earth, which is the object's weight, which depends on its mass. The hammer is more massive, it's heavier, it has more inertia, and it has a greater force acting on it. So these things balance out, and the hammer accelerates downward at a rate of 9.8 meters per second squared, or 9.8 meters per second per second. The feather is less massive, it's lighter, it has less inertia, and it has a smaller force acting on it, which balances out to make it accelerate downward also at 9.8 meters per second squared. What's up with that number, 9.8 meters per second squared? You don't have to memorize it for this course, but it's known as the acceleration due to gravity on Earth. It is the rate at which all objects fall due to Earth's gravity, without the effects of air resistance. It's all about gravity. That number depends on the size and mass of Earth specifically. Other large bodies, like planets or moons, have other values. For example, on our moon, the acceleration due to the moon's gravity is about 1.6 meters per second squared. This is why astronauts on the moon look like they're moving so slowly. The acceleration due to gravity is much smaller than it is here on Earth. The moon's gravity doesn't change the motions of objects quite as quickly. And hey, there's no air on the moon, so no air resistance. And in fact, in 1971, some astronauts took advantage of that and decided to test this idea out. Now, this concept was made known and famous by Galileo hundreds of years ago, and we have video footage of this experiment actually happening on the moon.
Well, in my left hand I have a feather, in my right hand a hammer, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
What do you know? The hammer and feather fell side by side at the same rate and hit the ground at the same time. So what I'm saying is that without air around, all objects on Earth would fall at the same rate. And some objects still do fall at the same rate, even with the presence of air. For example, if we drop two objects that are the same shape and size, they're going to need to push the same amount of air out of the way. So the same amount of air resistance should act on them if we drop them from the same height, given it's not high enough to reach their terminal velocity. And look, here's a video of somebody testing it out. He's got a ping pong ball and a ball made of steel that are the same size.
The tap of the ping pong ball hitting the floor is about the same time as the thud from the steel ball. Yeah, let me try it one more time. Yep.
He drops them from the same height, and yep, they hit the ground at the same time. All right, that's our talk on some common resistive forces, friction and air resistance. We discussed how our daily interactions with objects here on Earth, with the presence of things like friction, air resistance, and gravity, can make it seem like the natural tendency of things is to slow down and stop. But by isolating these influences and unpacking each one, we saw that really, the true nature of things is just to carry on without accelerating, whether that means sitting still or moving along at a constant speed in a straight line. We learned that friction is a force that acts to oppose the relative motion between surfaces, which sometimes makes our lives easier and sometimes harder. We also saw a sick life hack for when you need to open a jar of unsweetened applesauce. We talked about how things like air and water can resist the motions of objects, since a moving object needs to push them out of the way. We also learned that the two main factors that determine how much air resistance acts on an object is the speed of the object and its front-facing area. And remember that for most things on our scale, terminal velocity doesn't really kick in until something has been falling for a really long time. We even saw how and why all objects fall at the same rate when there's no air around to resist their motions. Basically, everything we've talked about in one way or another is evidence that confirms Newton's laws of motion. Number one, that an object won't accelerate unless there's an unbalanced net force acting on it. Number two, that when it does accelerate, its acceleration depends on the strength of that force and on the object's own mass. And three, that an interaction always results in force pairs between objects that are equal in size and opposite in direction. Cool. That's it for now. See you next time in our last instructional session. Looking forward to it.